Hey y'all, so let's say we're looking at the saturated water table and we want to figure out the saturation pressure at a temperature of 53 degrees C. And what we see on the table, there's data at 50 degrees C and a saturation pressure data at 55 degrees C, but nothing at 53. So one thing we can do is linearly interpolate between those two values. And what I mean by linearly interpolate, let's say there's, here we are at 50 degrees C, there's some saturation pressure, and at 55 degrees C, there's some other saturation pressure. In this case, the pressure is a little bit higher. And let's draw a line between the two. We're going to assume a linear dependence between those two. So here are the two data points we have on the table, the saturation pressures at 50 and 55 degrees C. We drew a line between it, and we want to figure out what is the saturation pressure when T is equal to 53 degrees C. So 53 degrees C would be somewhere right here between the two. We want to figure out what is P sat at this location. So the equation I drew up here is a general form for linear interpolation between two known data points. So the Y in this case is analogous to our saturation pressure, and X is analogous to the saturation temperature. So here's Y1. We could call this, let's call this point 1, and we'll call this point up here point 2. So Y is the saturation pressure we want. X here is the temperature at which we want to find it. So X would be analogous to T. So here's the analogous expression with pressures and temperatures. What I'll do is I'll plug in P1 and P2 and T1 and T2 and plug in a value for T, and we'll come up with the saturation pressure that we're interested in at a temperature of 53 degrees C. When I plug in numbers, I get a pressure of 14.4 kilopascal, which is between, and it's good, it's a check that I did it right, it's between 12.35 and 15.8 kilopascal. And now this assumes that there's a linear dependence between point 1 and point 2. And I'll show you that that's not rigorously correct, but that's the best we can do at the moment. To demonstrate this, let's recreate these numbers in ease, and I'm going to evaluate at 50 and 55 degrees. Let's evaluate these numbers. So here are two commands in ease that will recreate the tables in the back of your book. And instead of using water, it uses a function called steam IAPWS, and that's a more accurate equation of state than using either water or using steam, for example. So let's use steam IAPWS to recreate the steam tables themselves. So I'll run it, and what I come up with is P1 sat of 12.352 kilopascal and P2 sat of 15.763. And those are the exact same numbers for P-sat for point 1 and P-sat for point 2. However, so you'd think, well, alright, I'll evaluate at 50 and 55, and I'll evaluate this now at 53, and what I would expect would be 14.4 kilopascal. So here I've got a third line in ease. I'm finding the pressure, the same steam IAPWS, temperature 53 degrees C. And by the way, I'm calling a quality, I'm using a quality of 50% arbitrarily in ease. I could just as well do a quality of 0 or a quality of 1 if I wanted to. I'm just specifying, I'm just telling ease that I'm working with a saturated liquid. So I'll just keep them at 0.5 just because. So here is the P-sat, and I would expect, if we went back, I would expect P-sat, I would expect it to return 14.4. But I come back, when I run it for P-sat, what I come up with is 14.3. And the reason that this is smaller, this is the actual value. This is the value, if you wanted to be rigorously correct, this is what I would choose. But it turns out that instead of being a linear relationship between 1 and 2, there's a little bit of curvature here, and I'll exaggerate it in this case. But the real data look like this, and the actual value, if we don't use linear interpolation, the exact value is about 14.3 kilopascal. So linear interpolation makes our life easy, but there are small errors associated with that.